All right, hello everybody. Welcome. My name is Justin Clark and I'm an instructor with System Improvements, and today we're going to talk about equipment reliability troubleshooting and root cause analysis. What do these mean? How do we do them? And what are some structures to help us get rid of all those extra arguments on the back end? And this is kind of where the equipment troubleshooting framework in Taproot came from. Back in the 1990s, we had a lot of equipment reliability experts and troubleshooters keep saying that root cause analysis didn't solve their problems. And so Mark Paradise, a human performance expert that came out of the nuclear Navy, founded System Improvements, he got together with Heinz Block, a master global equipment troubleshooter with ExxonMobil. Both of them had many published studies and experience in their fields, and so when they got together, they wanted to solve this problem of why troubleshooting and root cause analysis were not working together. And so what did they learn? Mark learned from Heinz that equipment personnel were not fully troubleshooting equipment failures before they were finding root causes. They weren't proving how the equipment failed. What did Heinz learn from Mark? He learned that there were many ways after we prove how the equipment fails properly, technically, to find all of the reasons that allowed it to fail using more advanced forms of root cause analysis than 5 whys or fishbone diagrams. And so, to solve this problem, what do we need to do? It's actually both of those two steps. We need to troubleshoot the equipment first and prove how it failed, and then we need to do a proper, fully documented root cause analysis on those failures. And the big problem they were running into is that we were splitting the disciplines of human performance and equipment technical competence. And so, preventing these equipment failures, these reliability issues, takes looking at both areas. As engineers, I'm a mechanical engineer, we're very familiar with our equipment and getting into all the technical weeds, but those pesky humans, when we throw them into the mix, they cause some problems. And a lot of the issues we see have to do with both, so we need to look at both whenever we see an equipment failure. And so when we do first our equipment troubleshooting, it needs to be logical. And so those steps are listing all of the possible causes. What could be causing this failure before we ever put our hands on the equipment? Second, we narrow down the possible causes to see what are the things that we have not checked yet, what are the things that do apply to our system that we need to go either say yes or no to. We need to develop a strategy to gather that evidence so we don't lose any of it. And then finally, we go gather that evidence so that we can prove how the equipment failed. We never want to guess. We never want to hope. We need to prove exactly how the equipment failed, proving the true mode of failure. At that point, we will understand what happened, and that's the only point where we can jump into a root cause analysis. We can never ask why unless we understand what. And so a little bit deeper in this equipment troubleshooting side, one of my favorite authors, Sir Arthur Conan Doyle, who wrote the Sherlock Holmes series, one of the great quotes from that series is, "Eliminate the impossible and whatever remains, however improbable, must be the truth." If we have already checked the maintenance records, we don't need to go back to them. If we have already done the valve lineup, we don't need to go do it again. And so, once we have all of those possible causes, we list them out and quickly step through them. And then we're going to eliminate everything that doesn't apply. The things we don't care about, the things that aren't in our system, the things we have already checked, just get rid of them. We want to stay very disciplined and focused to narrow down that list of things that we actually need to go look for. Maybe this is all we know at the very start of an investigation. We have a pump fail a capacity test. We just installed the pump after an overhaul and it gave us 70% flow instead of 100% flow. From our incident here, failing the capacity check, the pump was previously removed for whatever alert. We fixed that problem, we found it, overhauled the pump, reinstalled the pump, conducted the maintenance test as we should after we reinstall equipment. And that's when we had our pump fail the capacity test. So there was something different, something changed that we need to find. One thing or many things. And so right now, we need to ask, what are all the possible causes that can lead us to failing the capacity check? And that could be everything from valve lineups to suction strainers to damaged piping to name all of the reasons that we can lose 30% of our flow for a pump. In this system, maybe we have 3 other pumps running in parallel. So we ask ourselves about inlet pressures, outlet pressures, water supply in the system, all the engineering flow stuff that some of us have learned about or work with on a daily basis. And so we want to ask, what are all of the possible causes for this failed capacity check? Now, if you're a pump expert, you may have been able to come up with all of these, and in fact, this is the list that Heinz Block came up with for this symptom of insufficient capacity. They just put this checklist together. Here's everything we need to look for insufficient capacity. So let's quickly check mark through them. What is possible? What is impossible? And we can quickly narrow it down. Now that might sound nice and comfortable in a webinar environment like we are right now. But if my refinery just went offline and we're on day 3 of an unplanned outage, we're already $5 million of revenue behind schedule, we're probably a little bit stressed. We're probably not going to remember every single one of these details, and we shouldn't expect that kind of performance from people under a lot of stress. And so we want to give them a list of possible causes to narrow down quickly. If you had paused it and were frantically writing down all of the possible causes, did you get all of these? Good thing to ask. So maybe in this situation, and this was a real investigation, we narrow it down to these 5. These are the only possible causes remaining. And so now, let's go tear the pump apart, put it in the exploded isometric diagram right on the shop floor so that we can see what parts failed, right? Wrong. We're going to lose some of that evidence. What if I needed to take an extra vibration cut? Was it rotating in the right direction? I can't gather any of that evidence because I've pulled the pump apart. So I need to start forming a strategy. Which one of these am I going to look at first? So don't jump the gun. Don't immediately pull it apart looking for that smoking gun. We need to plan out what are we going to look at first, second, and third. And if I find something like a valve lineup or maybe some kind of cavitation or maybe some kind of pressure issue that I don't have to take the pump out to fix, problem solved. Equipment back online as quick as possible. But if I do need to tear it apart, what retests do I need to make sure I do before I put the pump back in the system? Do I need to check, okay, we've taken the foreign matter exclusion fittings off, my plastic caps maybe, just to make sure I don't reintroduce any new errors. Okay, so we go and troubleshoot, and we get down to the point where we find that, okay, the mechanic installed the impeller backwards. Maybe you just put it on the wrong way. A lot of other systems will stop there because we found that the human made a mistake, slapped the mechanic on the wrist, put it back in properly, reinstall the pump, do better next time. Is that really what we want to do? Is that really going to prevent this from happening again? No. We need to understand what allowed, not why, what allowed our mechanic to install this impeller backwards. And so now that we have understood what happened, we installed the impeller backwards. That was our equipment troubleshooting. Now we need to start looking at the human side. We can start digging into what are all of the things about the training, the policies, the procedures, the experience, the qualifications of the mechanic. We need to look at human performance difficulties and start going down that path. We need to look at equipment difficulties. Maybe there was some extra failure or poor design that led to this issue. And then we never need to throw out the possibility of some kind of natural disaster or sabotage. So for every human mistake, we always want to look at these 3 categories to do due diligence. We let the evidence take us where it will. So we have equipment troubleshooting guides, but also in Taproot, we have a human performance troubleshooting guide. These are all the questions that Mark Paradise, the human performance expert, would ask about any human mistake, such as installing an impeller backwards, just to make sure that we look at everything we need to and eliminate everything else, just like back up in the equipment troubleshooting. So maybe we find, using the system, that there are some root causes, like our tools need improvement, that the situation wasn't even covered by the procedure, that there was no supervision when our mechanic did this overhaul, and that this also was his first performance of this overhaul. So that's good. Maybe we find these root causes, but if I just list these out here, that's not very convincing. You better believe that Vice President of Safety or Vice President of Human Resources, Justin, is going to argue with this. And so we need to be a little more evidence-based. Where do these root causes come from? Maybe they come from the evidence we gather during the interviews or during the maintenance record or the procedure review. In this instance, we found that the impeller was just a straight hole, and you can put it on either way. There was nothing there to make it really difficult to install the wrong way. That would lead us to tools need improvement. The rebuild procedure didn't even discuss this particular, put it on this way up. That can lead to other problems, and that did in this instance. The supervisor wasn't present, and this was, in fact, the first rebuild of this type that the mechanic had done. So he had never practiced it before, and we tossed them into this situation with really no preparation. And so even this is, maybe good enough for some instances. Vice President Justin is going to be arguing with this. And so we want to be even more disciplined and show our work. And so if we can all remember back to the horror days of high school math or college math, when we came across a test and we had just studied the Pythagorean theorem, if we write down the answer on the test, maybe we get partial credit. Maybe I had it just written on my arm and I was able to, sneak a look up my sleeve to see what the answer was. I can memorize this formula, sure, but what we're really trying to do is prove our work and show our work so that it is impossible for any reasonable human to argue. We want to make it really difficult to take off points in our math problem and in our root cause analysis. So we can just write the answer, or we can properly show our work. Not just showing every step, but why we took each step. What led us to take each step? What was our thought process? So that we can show step by step, here is how we got to our answer. That will make sure that not only our analysis is accepted, but also any corrective actions that we recommend will be accepted and approved by a reasonable Vice President Justin. Okay, so how does that look for a root cause analysis for our mechanic installing the impeller backwards? Here's what we want to do. We want to take that evidence that this is the mechanic's first rebuild of this type and show our work for how we got to the root cause. And so we want to have our analysis comments. So we can say this mechanic had only had brief training on pump overhaul and had never performed this job before. Our evidence from our snap chart, that shape right there, this is the mechanic's first rebuild of this type. And in the Taproot system, there's questions at each level that give us that justification. So we would say, was the training not repeated enough so that information could be learned and skills sharpened? That answer here is obviously yes, because it was the mechanic's first rebuild type. This is how we show our work that will lead us to that root cause of practice and repetition needs improvement. It's much harder to argue with this root cause when we see the step-by-step proof of the root causes. And we do that for each root cause. And that's the basics of how to do equipment troubleshooting and root cause analysis. The Taproot system is very structured and very fast to do that entire analysis, so that when we get to the end of our investigation and we recommend corrective actions based on objective root causes, it's very difficult to argue with them. And so all of that debate, all of that back and forth review that happens after a lot of other investigations simply doesn't happen. And so if you want to learn this process for how to properly show your work on equipment troubleshooting to prove how it failed, use all of those equifactor lists, use the root cause tree and corrective action helper to find real root causes, develop corrective actions that make sense and properly fix the issues that we've proved, come to one of our Equifactor courses. If you need to learn a lot more deep skills on how to interview and gather that equipment evidence, or do those maintenance record reviews, or analyze policies and procedures, we have a lot of other tools in our systems. Equifactor is one that we've already looked at, but we have a ton of other ones that you can use to just gather that what happened. The best place to come learn all of these tools is going to be the next Taproot Summit. And so we'll have a link in the description on how to learn all about that, but you can not just learn how to run the system, how to do equipment troubleshooting and root cause analysis, but see how everybody else in the world is running their systems, developing their own tables, doing their own root cause analysis programs, and grading the quality of their investigations. So I hope that was informative. I hope that was a good use of your time. If you want to learn more, give me an email, contact anybody at System Improvements, and we'd be happy to go into more detail. Thanks a lot. Have a great day.